So what we're going to talk about today is Lewis structures. This is the third to last part of chapter 6, which is our chemical bonding chapter. First, we're going to talk about a structural formula. So the word structure always means what makes up something or what something looks like or what the makeup of something is. So structural formula uses letters, symbols, and bonds to show relative positions of the atoms. It's based on Lewis dot structures. If you recall, we did Lewis dot structures with valence electrons in chapter 5, where you figured out how many valence electrons and you put them around the atom. And this is just another offset of that. So you see in this picture, this is an example of a structural formula. You have atoms here. You can see there's carbon and oxygen. And you're going to have lines connecting the element. These lines represent a bond. A single line represents a single bond, a double line, a double bond, and then if you had 3 lines, that would be a triple bond. Remember that each bond represents 2 electrons. So when you see a line, that means it's 1 bond, 2 electrons. So there's 2 total electrons shown here, and actually 4 shown here in the double bond. 2 on this line, 2 on this line. So what we're going to do in this set of notes is we're going to figure out how to draw these types of structural formulas, these structures which are called Lewis structures. So the rules, first you need to predict the location of the atoms, meaning which one's centered, which one's what we call terminal, or the ends of the atoms. You're going to find the total number of electrons available for bonding, and you remember that the only electrons involved in bonding are the valence electrons, or the ones on the outermost ring. You're going to determine the number of bonding pairs by dividing the number of electrons available for bonding by 2. We divide by 2 because each bond is made up of 2 electrons. And then finally, you're going to place 1 bonding pair, single bond, between each central atom and the terminal atoms. Remember, the central atom is the one in the center or the middle. The terminal atoms are the ones on the end. So the easiest way to learn this is just by looking at an example. So what we're going to do is step by step figure out how to draw a Lewis structure for the molecule CCl4. I will always give you the formula of the structure. From then you're gonna find the structural formula. So this is just the basic molecular formula, we call it. You're going to draw the Lewis structure or the structural formula from that. So the first step is to calculate the total number of electrons to be shown by adding the number of valence electrons. So remember, valence electrons are the only ones involved in bonding. So what you're going to do is you're going to look at each atom that is present in the structure. You're going to figure out what group that atom is in, that element is in, and from there it tells you how many valence electrons it has. Every one that I give you is going to be in the A group elements, the princess towers. So the group number is going to be equal to the number of valence electrons. So if we go back real quick, we see we have the element carbon, C, and the element chlorine, Cl. So I know that carbon is in group 4A, so it has 4 valence electrons, and chlorine is in group 7A and has 7 valence electrons. We know these 2 things just by looking on your periodic table. Now you see here I'm multiplying 7 by 4, and the reason I'm doing that is if we go back to the formula, this number right here is called a subscript, like kind of like below. This tells you the number of atoms of that element. So this 4 means that there are 4 chlorines, and then you see there's nothing here, which means there's 1. So what I'm going to do is say each chlorine brings 7 valence electrons, but since there's 4 of them, I'm going to multiply by 4 to get 28 total, and that's what I'm looking for, the total number of valence. So you multiply the number of valence of 1 times the subscript. Up here I didn't multiply by anything because it's just 1. To get the total, I'm going to add 28 and 4 to get 32 electrons. What this is showing you is when you draw your structure, either with lines or with dots, you need to be showing 32 electrons. You are not correct until there's 32 electrons being shown. The second step is to calculate the probable number of bonds. Notice the word probable. This is just something that guides you. This is not going to be absolutely this is how many bonds you're going to have. And we're going to do a couple where you're going to see where it makes sense. So a rule of thumb is to determine the number of bonds usually formed using this chart. You will always have this chart. So what you're going to see is group numbers of the princess towers, the A group, 1A, 2A, 3A, 4A. Notice we don't have 8A because They're noble gases and they're not bonding. And you're going to see the number of electrons used in the bond. This really isn't that important. What's really important is this row right here. Usually the number of bonds that form. So what this is saying is a group 1A element usually only makes one bond, 2A makes two, etc. and so forth. This right here and this right here is going to help you figure out how many bonds you need to show in your structure. So you're going to subtract the number of electrons calculated in step 2A from the number of electrons calculated in step 1 to determine the number of electrons shared. You're then going to divide that number by 2, because that's how many electrons are involved in a bond, to get the number of bonds. So if we look here, again, carbon is in 4A, so it's usually going to make 4 bonds with 8 electrons. Chlorine is in 7A, 1 bond, 8 electrons. Notice again, I'm multiplying these two numbers for chlorine by 4 because 4 was the subscript on the chlorine. So I would get 4 bonds total, 32 electrons. When I look at this information, if you see that this bond number and this bond number are the same, usually that indicates everything's single bond. But the more important part is here. You're going to add 8 and 32 to get 40. If you want to think of this like percent error, it's like actual minus theoretical. This is the theoretical number of electrons that should be used. And what I do here is I subtract 32. And if you recall, 32 was the actual number of electrons involved that we did in step 1. So when I do 40 minus 32, I get 8 divided by 2, always 2, because there's 2 electrons per bond. Now I'm going to find out that my structure most likely is going to have 4 bonds. Now, when you start drawing the structure, if that doesn't make any sense, then, that's an exception and we got to do something else. This number that you figure out is a probable. Probably it's going to have 4 bonds. You're going to figure out which atom goes in the center simply by its location. And what the rule is carbon is always the center, and you figure out which element is closest to carbon. In this case, you have a carbon, so that's automatically going to be the central atom. The chlorines are going to be the terminal. You're going to connect the atoms using lines. Remember that 1 line's a single bond, 2 lines a double bond, 3 lines a triple bond. So if I look, 4 bonds, carbon in the center, and I connect the 4 chlorines using all single bonds. So it worked out. I'm showing 1, 2, 3, 4 bonds, which is exactly what we predicted. The last part is, you remember, you have to have 32 electrons showing. So if I go back to this structure, remember each line only means 2. So this is 2, 4, 6, 8. I'm only showing 8 electrons. I'm missing electrons. I have to be showing 32. So the way you do that is you add them as dots. You don't do lines because a line means it's bonded. These electrons are not. They're just dots. So you'll see this looks very similar to the Lewis dot structures we did in chapter 5. Now to figure out where the electrons go, there's a couple ways you can do that. First, the most electronegative to the least is where you should put the electrons. The other way you can think of it is you start from the outside and work your way in. The last rule you have to remember is the octet rule, 8, 8, 8. All elements want to have 8. Remember that these are covalent bonds. So the bond that exists between this chlorine and this carbon, these 2 electrons count for both. So what I'm going to do is this. I'm going to find the carbon and I'm going to say, okay, how many electrons are around the carbon? 2, 4, 6, 8. That has a full octet. So I'm not going to add dots there unless I absolutely have to. If I go up to the chlorine, if I go back to this structure, right here it's only showing 2. I know chlorine wants 8, so what I do is add 6 dots, and now it has 2, 4, 6, 8. And if I do that all around and I count, you'll see, watch, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, which was the number we were looking for. If you do these correctly, they should, for the most part, work out exactly like that. Kind of like a perfect numerically when you do all your counts. A couple of exceptions here. First of all, drawing polyatomic ions. A poly, which means many, atomic atom. So a polyatomic ion is a many atom ion. You draw them like Lewis structures, except the more electrons are present if the ion is negative, less if it is positive. Resonance is a condition that occurs when you have more than one valid structure. It's possible, and it really only occurs when you have a double and a single bond together. It differs only in the position of the electron pairs, never the atom. So if you look at this picture, you have N and 3 O's. So what's going to happen is you need a double bond on the end. This is actually the charge, the ion. If you look at this resonance structure, you see there's 2 single bonds and 1 double bond. And the way this works, because it's just a carbon and 3 oxygens, is it doesn't matter where the double bond goes. This structure isn't any more correct than this one or this one. So when that happens, we call that resonance. It means there's more than one valid structure. And the way you actually would show that is with dotted lines for the double. Couple more exceptions. A molecule with an odd number of valence electrons, that's pretty rare, but sometimes you can just have a single electron there. A coordinate covalent bond is when one atom donates a pair of electrons to be shared with an atom or ion that needs 2. An expanded octet is just what it sounds like, when there's more than 8 electrons around an atom. These are all exceptions. These only happen when everything else breaks down. You're going to assume it's going to work out normally. Your math is going to be correct, but sometimes there's going to be some exceptions, and we will practice and talk about those.